This video introduces how to use Laplace transforms to find the solution for initial value problems. First, let's talk about Laplace transforms of the derivatives. So if a function's f is continuous and the function f prime, derivative f prime, is piecewise continuous on an interval from 0 to big A. And furthermore, let's suppose that there exists k, a, and m such that the absolute value of f of t is less than or equals k e to the alpha t for all t is greater than or equals m. As you remember, this is the definitions of exponential order function, as we have discussed before, right? Then the Laplace transform of the derivative functions f of t, f prime of t, L of f prime of t exist for s is greater than a. Okay, and moreover, the Laplace transform of the derivative of f prime of t equals to s multiplied by the Laplace transform of f of t minus f of 0, where f of 0 is the initial value of this IVP. So here's a proof of how we can derive this formula. It's a little long proof, but the thing is, briefly, you just put this Laplace transform into its definitions, and you break the interval into subintervals, and you integrate all of these integrals, right? So then, and then throughout the process, all the middle terms will be canceled, and only these three terms here left. And the last step is just take the limit of these three terms when a goes to infinity. And the result is the Laplace transform of the derivative of f of t equals to s times Laplace transform of f of t minus f of 0. Then if you want to find the Laplace transform of f double prime of t, the second derivative of f of t, you impose all the conditions and you repeat the whole process as how you have done on the function f and f prime. Okay, well, more particularly, you can see that the Laplace transform of f double prime of t equals to s times the Laplace transform of f prime of t minus f prime of 0, right? If you imagine this is f prime and this is f. Okay, and then from here, you know that the Laplace transform of f prime of t equals to s times the Laplace transform of f of t minus f of 0. And then you can simplify this side to get s squared multiplied by Laplace transform of f of t minus s multiplied by f of 0 minus f prime of 0. This is the Laplace transform of the second derivative of f of t. Okay. Generally, the Laplace transform of the nth derivative of f of t is given by this formula. Now, here's the steps on how to use Laplace transform to find solutions for initial value problem. Okay. First, you given a IVP, you apply the Laplace transform to the IVP from both sides, and you obtain an algebraic equation in the transform of the solutions. And then you solve the algebraic equation for the transform. Most of the time, you have to use partial fractions. And then you apply the once you solve for the Laplace transform of y, right, or f of t, then you apply the inverse transform to find the formula of the transform. So then you apply, you want to find the inverse of the Laplace transform to find the original functions, which is the solution to the IVP. There's a remark that you want to pay attention to is when you use Laplace transform to solve IVP, the initial values have to be at t0 equals 0. If not, we need to manipulate algebra, if possible, to convert the non-zero initial value to zero initial values. Because if you pay attention to the form, right, this is the Laplace transform of the first derivative, and you have to use f of 0. And this is the Laplace transform of the second derivative. And again, you have to use f of 0 and f prime of 0. So all the initial values have to be at 0. Okay. All right, let's do an example. So you're given this simple first order differential equation with one initial value. Then the first step is you want to apply Laplace transform to both sides. Okay. And we know that the Laplace transform of is linearity, so we can break this into two different Laplace transform in terms of y prime and y. And the Laplace transform of 0, it should be 0. Okay. Then using the definitions, we know that the Laplace transform of y prime will be s times Laplace transform of y minus f of 0, and in this case, f of 0 is 1, plus 2 Laplace transform of y equals to 0. Then the next step is you want to solve for Laplace transform of y. And then by grouping like terms, Laplace transform of y together, you have s here plus 2. Okay. And then you move 1 to the other side. It's equals to 1. So the Laplace transform of y will be 1 over s plus 2. All right. Now, there's a time when you can use the inverse Laplace transform. So you have to find y by inverse this. The next thing is finding the inverse of Laplace transform, right? Inverse of this. Equals inverse of the function 1 over s plus 2. Okay. And from the left side, you find y, and the right side, you find the functions. Take an inverse. In this case, as we know that s plus 2, 1 over s plus 2 is a form of e to the alpha t, where alpha equals to -2. So that means y equals to e to the -2t should be your solution. Okay. Recognize the form. This is e to the alpha t, and you have 2 here. That means alpha equals to -2. So e to the -2 should be your solution. So as you can see that using Laplace transform, you can find the solution to this IVP. You don't have to solve for constants because you already found it. How about the next example? Here you have, again, first order differential equations, but this is a non-homogeneous equation. So let's see how we can tackle this problem. Again, first we just apply Laplace transform to both sides. Then I break it down, right? Using linearity. And I have to find the Laplace of this, of the right side. Well, let's see. This is the functions, products of t and e to the negative t. Then we can use one of the theorems. We can find the Laplace of other side. So I break this into 3 t e to the negative t. Other side, we can find the Laplace of e to the negative t, which is, so this is f of s, right? Which is 1 over s plus 1. And then we find, because it's multiplied by t, then you find the negative derivative of d over ds. So that would be 1 over s plus 1 and square. Usually it should be negative 1, 0 minus 1 times 1 and negative, so 1 over s plus 1 square is the Laplace transform of this function and multiply by 3. So you have 3 over 1 plus s plus 1 square. Okay, and from here we know that Laplace of y prime is s times Laplace of y minus 2 Laplace of y equals to 3 over s plus 1 square. Then we solve for Laplace of y, and we group Laplace of y together. So you're gonna s minus 2 equals to, oh, you know, I'm missing something. I'm missing f of 0 here. Okay. So you should have minus f of 0, which is 1, minus 2 Laplace of y equals 3 over s plus 1 square. All right, now I group this and this together. I move this over here, equals to 1 plus 3 over s plus 1 square. And again, to solve for our Laplace of y, we divide everything by s minus 2. Okay. Well, the next step is we need to find the inverse of these functions, right? The inverse of 1 over s minus 2 is simple because this is e to the alpha t, where alpha equals to 2. So this should be e to the 2t. Okay, how about these functions right here? In these functions, because we have a product of two functions in the denominator, we need to use, and we don't have any Laplace transform that in this form. So we need to break this fraction into multiple fractions, and we have to use partial fractions technique. Okay. So let's use here. I want to do it on this side. So let's say this, let's do it on this side. Okay. 3 over s minus 2, s plus 1 square. If you want to do it partial fractions, then you have 3 different terms here in the denominator, and you have just a constant here. So you're going to break it down into 3 different terms. The first term is s minus 2. The second term is s plus 1. And the last term is s plus 1 square. Okay, because you have constant on the only a constant, in the numerator, then all the numerators of all these terms are also constant. Okay, well, the next step is, as you remember, we have to combine this together in terms of ABC, and then you solve for ABC. So then the sum here will be equals to this fraction. So if we combine these three together, I will have A S plus 1 square is a term that I'm missing, plus B S minus 2 and S plus 1 plus C S minus 2, right? You just multiply all the missing terms to each of these fractions, so then it will have the same denominator. And then I just distribute them all out. Plus 2AS plus A plus B S squared plus minus BS and minus 2B plus CS minus 2C. Okay, and then at this point, I want to group like terms together. So A plus B S squared, and you have AS, BS, CS plus 2A minus B plus C S, and then constants, constant, constant, plus A minus 2B minus 2C. This should be C. Okay, so this is the numerator. We found the numerator, and we need to force this numerator equals to 3, which means this term has to be equal to 0, right? This term has to be equal to 0 means A plus B has to be equal to 0. Also, this term has to be equal to 0 because you don't have any S squared, you don't have any S on the other side. That means 2A minus B plus C equals to 0. And this term here is a constant, and it has to be equals to 3. 2C equals to 3. And from here, we'll have 3 equations, 3 variables, we just solve for it. So I'm using substitution. So solving for B equals A equals to negative B. If A equals to negative B, then this should be negative B minus 2B, negative 3B plus C equals to 0. That means C equals to 3B. Okay. So everything A and C are forced in terms of B, then I can replace those into A and B here to solve for A and C here to solve for B. A here is negative B minus 2B is negative 3B, negative 2C, and C is 3B, so negative 6B equals to 3, means B equals to negative 1/3. Okay. If B is negative 1/3, then A equals to 1/3, and C equals to negative 1. So we've just found A, B, C, so then you plug A, B, C in here, it will be equals to this fraction. Okay. So from here, I can, let's see, rewrite this in terms of these 3 fractions up here. It's gonna be 1 over S minus 2 plus A 1/3, 3S minus 2, right? B is negative 1/3 minus 1/3, S plus 1, and C is negative 1 minus 1 over S plus 1 squared. Okay. And then this term, you can combine them to be 4 over 3 S minus 2 minus 1 over 3 S plus 1 minus 1 over S plus 1 squared. And you can recognize that this is e to the 2t, 4 over 3, okay? And this is the form of, again, e to the alpha t, where alpha equals to -1. So it's going to be 1/3 e to the negative t. And this is the form of, as you remember, s plus 1 squared, right? This is a form of 1 over s squared, and then you move it 1 over s minus plus 1 squared here. So this is the form of t, and this is multiplied by e to the negative t. So this is the inverse of this function should be negative t times e to the negative t. So this should be your answer. All right, I should rewrite it in better. So the answer is y of t equals to 4 over 3 e to the 2t minus 1 over 3 e to the negative t, and minus e to the minus t e to the negative t should be your final answer. Using Laplace transform, again, you don't have to, solve for constants because you use the initial value inside this form, right? So then you don't have to use a constant. Solve for constant, you can, once you solve, use the Laplace transform, you find the particular solutions directly here. Okay, so here's the two examples of how to use Laplace transform to solve first order IVP. And for the second order IVP, you just need to use this formula here to translate Laplace transform into a differential equation into Laplace transform. And again, you just need to solve for the Laplace transform and then find the inverse functions. So then to find the final solutions for the IVP.